So we've been developing methods of estimating random variables, and in the example we just covered, we had a linear estimator that was attempting to estimate the random variables in a sequence, or in other words, a random process. And we also knew something about that. So in this case, we decided to use as our inputs into our estimator the current observation and previous observations coming out of in this case, a communication channel, but it could be basically any system. And so we then wanted to minimize the error. I think last time we actually defined the error slightly different to introduce a delay possible. For now, we're going to ignore that delay and just have n naught is equal to 0. We can always introduce it later. And d hat, our estimate, is h transpose, which is our filter, times y. The boldface y is a vector that contains the most recent m plus 1 samples. We can also write this as a convolution type equation. It's the same thing when we have there we go, y defined as that vector and h defined as that vector. So apparently in my restoring what I had typed previously, I did it in the wrong order. So let me go back and first note this gray note up here. I've switched notation to use a lowercase h instead of the uppercase on the previous page. And that is because in this particular case, h is a vector. There might be cases where h is a matrix. I try to keep vectors as lowercase bold letters, matrices as capital letters, and scalars as lowercase not bold letters. I know sometimes it's hard to tell with handwritten notes, but I try to use a thicker pen when I do that. Also note that we're going to be developing, as you can probably see from the title, the Wiener-Hopf equation, and we're going to be doing it for real data. I actually toyed doing it with complex data, and you get a result that's very similar. I'll show that result at the end. It's just that it's a lot more bookkeeping to track where things are going, and I didn't want to lose the thread of where we're going with this. You may also recall that last time we designed our filter according to the criteria that we wanted it to exactly cancel the impulse response of our channel in this communication scenario. So we had h convolved with g was a time delay delta. This time we're going to not try to customize that. We're actually just going to try to minimize the expected error directly and see where that takes us. Although it's not required, it certainly makes it a lot easier if we assume that the system we're looking at is wide sense stationary. So in the case of the communication system, that means that our g isn't going to be changing, and the statistics on our d is not going to change, and that the noise, the added noise, isn't going to change. So we'll find that this is impractical, but let's start with this and then we'll have the tools to move on. So the first thing we're going to do is let's define an expected error as essentially the expected value of the error squared. This isn't the only error metric that we can use. In fact, this is not the only one that's used, but it's a very common one. Since we are dealing with a stochastic process, expectations make a lot of sense. And squared error is a common metric because it correlates with the amount of energy in our error signal. And so knowing the expected squared error, we can calculate things like the signal-to-noise ratio and other useful quantities. This, of course, can be expanded as d of n minus d hat of n squared. And now the job is just going to be go through and expand this out and go about minimizing it. Now there are also a couple ways of minimizing this. One is by completion of squares, and the other is by just straight calculus. So we're going to go the calculus approach. So our first step is just to multiply the squares out, and since expectation is linear, we get this sum of expectations. Next, by substituting our expression for d hat as h transpose y, we can simplify things a little bit further. One thing to note in this last term here, if we just did h transpose y for both d hats, then we'd have something that looked like h transpose y, which doesn't make a lot of sense, or at least it's harder to work with. But it turns out that d hat is a scalar, and you can take the transpose of a scalar without affecting anything. When we do that and then expand it out, we get this h transpose, and then we have a y transpose, and then h. This is the more common quadratic formulation that we would expect to see. And we have our expectations in there. Now we can simplify this by defining a few terms. I've already done so in the very first term of the equation. That is that the expected value of dn squared, if it's stationary, is just sigma squared d. This assumes also zero mean, so that would be implied in there. We're also going to define the quantity ry, so r is capital letter, it's a matrix. Y transpose, the expected value of that. This is going to be an outer product, and it's called the correlation matrix. And then we'll define r dy, and this is a vector that is the cross correlation between the scalar dn and the vector yn, like so. Okay, so with these things defined, we obviously here have this expectation is going to be r dy, and this expectation is going to be our capital R of y. So I should note, in order for these things to hold, a very important assumption, and that is that we have zero mean random processes. Okay, so to minimize this expected squared error, we simply take its derivative with respect to h and set that to 0. And the sigma d squared term, it's not a function of h, so its derivative is 0. We have minus 2 rdy, and then plus 2 ryh. Now it's likely that you haven't done derivatives with respect to vectors and matrices lately, so I've put here a link to a very handy resource. I hope it's there permanently. It's been there for many years. It's called the Matrix Cookbook, and it's basically a how-to guide to do things such as this. How do you take derivatives with respect to vectors and matrices and the like? So if I recommend that as a good resource. Well, now we're getting to our final solution. By setting that equal to 0, we can divide out by 2, put our rdx, or our rdy rather, on one side of the equation, and our ryh on the other, and this is called the normal equation, also known as the Wiener or Wiener-Hopf equation. Once we have this equation, we can solve for the optimal filter. H is simply going to be Ry inverse times R dy. So this was the solution for a real system where we have real inputs and real observations. What happens if we have complex observations and complex inputs? Well, it turns out that the Wiener-Hopf equation is going to look the same for complex data, except that our matrix and our cross correlation are going to be determined slightly differently as follows. So instead of the transpose, we use the Hermitian transpose, and the second argument in RYD is conjugated. Once we've done those, then H will be calculated using the exact same normal equation that we saw up above.